Okay, so here's a fun question for you. What do, say, a cooling cheesecake and the planet Mercury actually have in common?
Hey, it sounds odd, but the answer is pretty cool. They both shrink as they cool down.
Exactly. And that's what this deep dive is all about today. Mercury's continuous shrinkage. It's been happening for, what, 4.5 billion years?
That's right, since its formation. And our mission today is really to unpack the latest science that gives us a much clearer picture of how much it's shrunk and, what that tells us.
So let's get into it. Why does Mercury shrink in the first place?
It's all about heat loss. Mercury's core is constantly cooling, losing heat out into space. As the inside cools and contracts, the rocky surface has to adjust.
Just how? Like, it just gets smaller smoothly.
Not quite smoothly, no.
Yeah.
It causes the crust to basically buckle and break. This creates huge cracks or geological features called thrust faults.
Crust faults, okay.
Yeah, think of them like wrinkles or seams on the planet's surface. Some are massive, like the Enterprise Rupes Fault you can see cutting right across a big crater called the Rembrandt Basin.
Wow. So we can literally see the evidence of this shrinking.
We can.
Then why has it been so hard to measure the total shrinkage? What was the big challenge there?
Well, that's been the tricky part. Scientists tried estimating it by looking at these faults, mapping them out.
Makes sense.
But the estimates were all over the place. I mean, really wide ranges. Some suggested the radius shrank by only about 1 kilometer. Others said maybe up to 7 kilometers.
Hold on. 1 to 7 kilometers? That's a huge difference. Why is such a discrepancy?
Exactly. It was a major problem. The issue is that those older methods, they really depended heavily on how many faults you included in your map or your data set.
Ah, okay. So more faults counted, bigger shrinkage estimate, less faults, smaller estimate.
Pretty much. It made it really difficult to nail down a reliable number. The results weren't consistent across different studies or different data sets.
Right. That sounds frustrating. But now there's a breakthrough, some new research.
Yes, exactly. From Stephen Loveless and Christian Klimczak, they published this in AGU Advances, a top journal, and their approach is, well, fundamentally different.
How so?
Their method cleverly doesn't rely on counting every single fault.
Oh, so what does it do instead?
It focuses on the scale of the largest faults. They measure the amount of contraction shown by the biggest fault in a data set, and then using some smart geological modeling, they scale that effect up.
So, like, measure the biggest wrinkle to estimate the total shrinkage of the fabric rather than counting every tiny crease.
That's a great analogy, yes. And the beauty of it is the consistency.
Consistency. How consistent are we talking?
Well, they tried it on 3 different data sets. One had only 100 faults, another had over 600, and one had nearly 6,000 faults.
Okay, vastly different amounts of data.
Hugely different. But no matter which data set they used, their method consistently pointed to about 2 to 3.5 kilometers of radius reduction caused specifically by this faulting process.
Wow, okay. That's much tighter than 1 to 7. So that's the shrinkage from the faults, the wrinkles.
Yeah.
Is that the total shrinkage?
Not quite the total shrinkage, but a really important piece. We need to combine this new faulting estimate with estimates of shrinkage from other ways Mercury cools and contracts internally.
Right.
And when you put it all together, the best overall estimate now for the total reduction in Mercury's radius since it formed is somewhere between 2.7 and 5.6 kilometers.
Much more refined.
Yeah.
So what's the big takeaway for us for understanding planets?
Well, it gives us a much better handle on Mercury's thermal history, how it's cooled over billions of years. But it's bigger than just Mercury.
How so?
This same method, this clever technique focusing on the largest features, could potentially be used on other planets with similar faults. Think about Mars, for instance.
Ah, interesting. So it could help us understand the geological activity and cooling history of other rocky worlds, too.
Precisely. It's a new tool in the toolkit for planetary scientists. So, to recap, we now have a much clearer, more reliable picture of Mercury's incredible shrinking act, thanks to this innovative approach.
It really makes you wonder, doesn't it? If this method works so well for Mercury, what other planetary secrets are waiting to be uncovered on places like Mars, revealing more about how these worlds change and evolve right across our solar system?